The Miscowaubik Club, located in Calumet, is the only private club in the Keweenaw and one of the best restaurants in the area. They are open most evenings for dinner and hold many special events there, such as parties and weddings. About a year ago, they replaced the ceiling in the main entrance and in their bar due to damages. What was once an acoustically tiled ceiling has been replaced with a plastered or drywalled ceiling. The club now has a noise problem, where people are sitting in the bar having a good time, but their conversations are carrying into the dining area. The people in the dining area are complaining that the people in the bar are being too loud, and that they'd like to enjoy their nice dinner in a quieter atmosphere. Here's a drawing of the Miscowaubik Club bar area and dining area. Bar area is on the right, the dining area is up on the left, and each room is filled with a bunch of tables. The biggest noise problem for the Miscowaubik Club is a group of Italian men who sit at the table with the red X. Their sound goes directly through the opening. It gets directed off of that wall as a reflection, and it also gets directed from this big bay window and also gets redirected through the opening. And it annoys all the people sitting in the tables in the dining area. We measured T60 in both the dining area and the bar area. The circles are the speakers, and we measured at the 6 locations where the X's are. We also took SPL measurements. We placed the speaker at the table where the noise is a problem, and we measured at various locations in both the bar area and the dining area.
This is Keegan. I'm just going to run you through the MATLAB code that we use to post-process all of our data. So to start, up at the top here is just some importing using XLS read. It's not very exciting. We locate or calculate the T60 times as well as the room absorption. So when we started this project, we thought maybe it was a reverberation or a room absorption problem, so we were investigating the necessary room absorption to meet some target sound pressure level in the dining room area. We later determined that that wasn't actually the problem, that it was a transmission loss problem. So starting here, we have a couple different calculations. One looks into a single layer system, which is what this small block of code does, and then we investigate a multi-walled system, which would just be 2 curtains hanging a certain distance apart. So you can specify the distance, the mass density, the surface mass densities of each curtain, and then it calculates all of this for you. The important thing is what it gives you in the end. So once this code runs, it'll just take a second. It's going to give us the room absorption shown here, the T60 time of the room, the surface mass density needed to achieve what we determined to be the target transmission loss, which is generated under the assumption that we want it to be 10 dB less than it is currently in the dining room when there's a loud noise source in the bar area. So that's what this green curve is in the top right, and it's a relatively constant 10 dB of transmission loss. So this blue curve is what we would expect to see using the mass law prediction for a single layer curtain. The red curve is actually a piecewise function, and it's the same mass law except it's for a multi-walled system. And this curve changes dramatically based on the input parameters, which we saw here. So these input parameters will change this curve, and this is just an example. The one we actually ended up recommending to the Miscowaubik Club has a better attenuation or transmission loss at these low frequencies.
Alright, we are testing insertion loss and noise reduction of the curtain material that we ordered from Rose Brand.
It's a 32 ounce curtain, 100% cotton, and it's 100% nap-down model. We're going to use it with various combinations in this partition to get the insertion loss and noise reduction.
So we're going to take the curtain material and put it up against the surface here and cover the opening entirely with 0% gap. We're going to use some tape to adhere it to the opening. We have a microphone inside the anechoic chamber and 3 microphones inside the reverberant chamber.
And you should make sure that there will be no gap between the curtain and the wall, so that it will be a perfect condition.
And after we test that, we're going to double up the layers. So we will have one curtain on the inner opening and then one on the outer opening as well. So we can test the 2-layer effect with a gap. So here we are setting up a 2-layer test where the curtains are pressed right together, no gap in between. And next we're going to put 1 layer on the inside and 1 layer on the outside with a gap of 8 inches in between.
So this is the code that my team used to analyze the transmission loss results that we did in the anechoic and reverberant rooms on the 6th floor. And so essentially all it does is measure the sound pressure level in both rooms, because we didn't want to do an actual transmission loss measurement because that's very difficult. So we did both insertion loss and noise reduction. So this pulls the sound pressure level in the source room and then calculates the noise reduction seen across the barrier. And using the SAE J1400 method, we came up with this correction factor as well as a calibration transmission loss value, which then we could apply to all of the noise reductions to get a theoretical transmission loss. That's all just math. So once you plot all of this along with the octave band content, you come up with these plots, which I will zoom in. So this is the single, double, and triple layer curtains with no spacing in between. So the yellow is the has the treatment on it, and then the blue is with no treatment. So there's significant noise reduction at all of these, except that it increases as the thickness of the material increases. But you'll notice, so this isn't a frequency content. The axes aren't labeled very well, but this is frequency. So at these low frequencies, even a triple layer curtain doesn't really attenuate, or it doesn't really cancel out any noise. And the same is true with this graph. The best that we get is 2 double layer curtains spaced 8 inches apart, but we're still not getting any transmission loss at this low frequency. The reason for that is because the background level in the anechoic room is not 10 dB less than the measured sound. So at those low frequencies only. So we can't trust any data below 100 hertz. So this is the calculated transmission loss using that SAE method, and it's pretty consistent, like we expected. The dual layer curtain spaced 8 inches apart is the greatest transmission loss, with this bottom curve here being completely open with no barrier. So this will be the treatment that we recommend to the club.
To sum everything up, we and the Miscowaubik Club know that a solid door would be the best solution to their problem. It would block out the most noise for sure, and it might even look the nicest. However, they don't think that's very practical because of installation purposes, as well as impeding the flow of traffic between the bar and the dining area. As Keegan mentioned, we're going to recommend that they buy a bunch of this 32-ounce curtain material and have a 2-layer gap, 2-layer curtain setup with a very small % gap around the perimeter. We would have liked to have implemented our solution at the Miscowaubik Club and done some testing to validate our results, but the Miscowaubik Club wasn't quite ready to spend the $600 or $700 it would have taken to install these curtains. Overall, we thought this was a really fun and unique project to work on, dealing with room acoustics and transmission loss. Hopefully someday the Miscowaubik Club installs our curtain solution, and the people in the dining room can enjoy a quieter meal.